topic by topic. Today we're going to start having a look at circular motion. Now, circular motion's not really very difficult from ordinary motion, that is motion in a straight line, but there are a few things that cause a little bit of problem with this. So let's go and have a look and see what sort of things we expect to cause problems. Now, what I've got is a simple idea of an object moving in a straight line, and that's easy. We know that we'll call the velocity. It's in a straight line, it's going in a particular direction. But what happens when we get this object to go round in a circle? Yeah, I managed to put my circle templates down, so we'll do it the hard way. So we've got here going in a circle. Well, it can't have a velocity because this velocity is in a straight line. So the velocity here is basically constantly changing. And if it's constantly changing, then the change in velocity I would call an acceleration. So let's start having a look at what's going on here, because we've got to try and measure this, and this we need to do as an angular measure. Now, for many people, we stick to measuring angles in degrees, like sort of the old 90 degrees for a right angle, and we measure the angles in a circle 360 degrees. But there's something much better to do this with, and the mathematicians use this, and these are called radians. Now, what is a radian? Well, simply put, a radian is a measure of the radius. So let's take my simple circle and let's draw in around here a simple circle, and this distance here is in fact the radius. And what we can do is let's just draw in from the center of the circle the radius. So here we are with my radius. If I can now measure that distance and go round the circle that much, so whatever that distance is, but this time going around the curve, and I can approximate that. I set it back to 3 centimeters. So if I were to follow that round roughly 3 centimeters, I get to a point somewhere along here with my circle, and this is also my radius r, but this length here is also my length r. So that is what basically we've got an idea of what is a radian, and we measure this. There we are, a radian. So we know from simple maths that if my radius here equals r, then my circumference is going to equal 2 pi r. So if we sort of work out what the angle of a whole circle would be, Well, we can use that to work it out. So it's going to be 2 pi r divided by r. They cancel out, and so we can say that my circle is going to be here 2 pi radians. One complete revolution of this circle equals 2 pi radians, and that also equals 360 degrees. So we've got here some sort of measurement. Well, if 2 pi radians is 360 degrees, then it follows that pi radians is going to be 180 degrees. And if we've then got pi divided by 2 radians, and we often use just a little C up there, like a degrees symbol, but now as a C, that's going to be 90 degrees. Pi divided by 3 radians would be 60 degrees. Pi divided by 4 would be 45 degrees. So we've got lots of ways of doing things and measuring them out. I suppose the other useful one is pi divided by 6 radians would be 30 degrees. So we've got some idea about what radians are, so that we can work out all types of bits and pieces. And many times we can actually calculate these by having a look at perhaps something like a clock face to work out how fast a hand might travel around a clock face. Well, we'll try that perhaps in a minute, but let's have a look at some other things about radians and about circular motion. So our circular motion here, we know that our speed equals my distance times the time taken, basically. So we've got my circle, and with this circle here, it's going to be basically, well, my speed is going to be the distance. Well, my distance is the circumference, so we can think of my speed equaling my circumference times the time taken. Well, what is my circumference? Well, we know that's going to be 2 pi r, and here this is going to be circumference divided by time, wasn't it? Here, so we've got here the speed is going to be my distance, yeah, times my time here, and then if I want to try and work out here my speed, is going to be, yeah, it's distance divided by time. I don't know what I'm doing. It's going to be that divided by the time taken. There we are. So I've got here a measure of my speed. So I can't do velocity, but I can measure speed. Now my circular motion we can call something special. Now I want to use the word velocity, but I can't use the word velocity, so we come up with a new term, angular velocity, and we give that the symbol this W. Right, now the angular velocity is the angular rotation that occurs each second. So if my velocity, my speed is going to be that, then my angular velocity is going to equal 2 pi divided by the time taken. Now that gives us two basic formula. I've got here v equals 2 pi r over t, and we've got this idea of angular velocity. So if I want to work out what my velocity is, it's going to be my angular velocity times by my radius. And what else do we know? Well, we also know from doing some of our work with waves that the frequency equals 1 over t, the period. And this period, this t, is the same as that time there. So we can say that omega here can also equal 2 pi times the frequency. So this is giving us a few equations that we can do. So I've got that, rearranging this one, I can say omega equals v over r, and I can also see that this here is going to be my angle that we have travelled through divided by the time. So that gives us a few bits and pieces that we can actually look at, and what we then need to do is try and have a look and see what happens with circular motion. So let's see if we can explore a couple of things with circular motion. And what I'm going to do is I'm going to have a look at a couple of experiments, but I'm going to start with an experiment on the floor. And this experiment on the floor, I've got, I need to move the cable out of the way for the computer and whatever. Now let's have a go, see what we can do. I've got here a hoop and I've got a ball bearing, and what I'm going to do is I'm going to throw the ball bearing around this circle, and we can see it goes in a nice circular direction. Let's try it again. But if I let it go, it comes out in a straight line. Let's try that one again. It's going round. I'm now going to release it, and it moves off in a straight line. We'll just do that once more. So we've got this going round. I'm not trying to make it go too fast. It did collide with me. Let's release it. Banged it a little bit and it went off. in a straight line. And it does. It goes off in a straight line. And this is reminiscent of something like a roundabout. Do you remember the roundabouts? You've got a roundabout and you're a child on a roundabout, and as a child on a roundabout you're spinning round and you're standing somewhere on this little roundabout as it goes round and round, and you hang on to the little rails that are inside this roundabout, and you feel like you are being thrown out in that direction, but you're not really. You see, if you actually try the physics and you literally get off of this roundabout, then you won't go off at 90 degrees here, but instead you would carry on in the direction you were travelling, and you go off in that direction. You feel like you're being thrown out, but in fact you're basically trying to carry on in a straight line because of velocity. Well, let's have a look at what we can see about forces going along with this, and we'll have a look at another little experiment that does this. I'll just try and pick the ball bearing up. Now, some of you may be familiar with this experiment. It's probably one of the more dangerous experiments that we do in physics, and what I've got is a rubber bung attached to a piece of, here this is nylon thread, and attached to this inside I've got a spring with a little marker on it, and I can adjust where that goes. Now what I'm going to try and do is I'm going to put this at a certain point, and let's say I adjust this here to 5 on this scale. So I'm going to put my little bead, which you can see, at 5. We can lock this off, and then what I'm going to do is I'm going to spin this. We'll move the camera back because it's going to get a bit dangerous here, and as I spin it I want to make sure the radius is always here the same length, and so what I'm going to do is I'm going to spin it, and as I spin the spring's going to get stretched, and we're going to make sure I get up to the 0 mark here, and as I get up to that 0 mark then we can see. So first of all I'm going to measure how long is this piece of nylon. So I've set my ball to 0, and here we can see the length of this is set to 77.5 centimetres. What a lovely number. Right, okay, so I've got that set to 77.5 centimetres. Okay, I'm going to set this now with this bead at a position of 5, and now I'm going to spin this, and what we're going to do is we're going to make sure I've got my chair out the way, and I'm going to spin this, and I'm going to try and leave this here so you might be able to zoom in and have a look at this. But what I'm going to do is I'm going to give this a bit of a spin. Here we go, making sure everything's clear. Here we go. So I'm spinning it faster and faster, and at that point I've got my little bead here at 0. When I point it, I can't seem to spin it at the same time. So what we now need to do is to measure how many times this bung goes around in, let's say, 10 seconds. So what we now need to do is to stop this before I kill myself or somebody else, and we're going to try and measure now how much this is going to sort of move up here. We're going to move it that much, that force. We can try and measure that force in a minute, and we can work out our basic speed. If we know its length here, which we do, the radius, and I can take a choice of either measuring it to the string, or I can measure it to the end of this bung. That's right, the camera didn't move with me. I expected it to do it, and it didn't. Right, so we can measure this length, which you can just about see probably. We know that length, and if we know the force on this, and we know the number of times it spins. So what we need now is a stopwatch, which we've got, and we're going to get this spinning, and on the command go, my son's going to start the stopwatch, and I'm going to try and count, and maybe you can count with me, try and make sure I don't make any mistakes. Right, so let's give this a bit of a spin, and I've got to get it going enough that it's going to be at the right speed. So that was a little fast. It's a little slow. Right, there we have it. So what I'm going to do is try and count the number of times we go. Ready on the stop clock. Here we go. Ready, steady, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And 30 spins gave us 16.92, and it did clunk me on the head. It's one of those problems. Right, so let's write that down. I did 30 turns, and that was 16.92 seconds. I suppose we ought to do that once more, just to sort of verify I've got that one right. And I did 30 turns because I'm hoping enough turns here is going to give me a more accurate figure, because I'm not really that confident about keeping this going exactly the right position. This is where you need someone else to sort of time this for you and do that. We can either time for 10 seconds, or we can do it for how many turns. I think turns and counting the number of seconds is probably a better system. So I'm going to make sure that this is set right. Now that was set at 4 last time. I'm going to leave it at 4 this time. Right, let's see what we can do. So that's about the right distance. Ready, steady, go. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to do that again. It was coming too much. I'm making it go too fast. I've got to try and look at one place and not look at two things at the same time. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 23, 24, 25, 26, 27, 28, 29, 30.
15.92.
15.92. Now, given the accuracy of me spinning this, that looked pretty good really. So what I'm going to do is we're going to adjust this, so I'm going to spin it faster. This is going to get dangerous. So what I'm going to do is I'm going to set this now to 10. I've got to spin it a lot faster, because now to get it up faster I've got to increase the spin. I'm hoping I can get up to 10. I've had my shredded wheat this morning, so it should be okay. Let's see if I can get this going up to 10. And that's at 10. It's going to be hard to count. Here we go. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17. No, I lost it. We'll do it again. Try and get this going. The camera can barely catch this. And go. Stop. And we got 11 seconds there. So it was a 30 turns, approximately 11 seconds. Now something else I can try and do with this, which is slightly safer, is what I can do is I can change the length of the string. But first what I'm going to try and do is I'm going to work out what force goes on here. So I'm going to adjust this back to where it was at 4. And there is 4 on this scale. Hopefully you can see a little ball there. It's at 4, and I moved it to 0. Now what mass did I need to put on there? So let's just get out some little slot masses and let's see what's needed to stretch this spring out that far. Well, 10 is not going to make any difference, so let's start with a decent number. No, it's not going to go on. So let's put on here 100 grams, and 100 grams has taken this to 2. So let's try 200 grams, and that's taken it here. So 200 grams is the amount of force that we've needed to put on there. So 200 grams, we can work that out in newtons. So we've got 200 grams there. So to get our extension, that distance, 30 turns, those numbers, and then that was set at 4, this was set at 10. To do 4, that needed a force of 200 grams. So putting that simply, that's 0.2 kilograms times 10 gives us 2 newtons worth of force. It seemed like an awful lot more than that when I'm trying it. Let's make the string shorter. Now, one way of trying to do this is to wrap this nylon thread round, and what I'm going to do is I'm going to put an elastic band around this, and I'm going to hope it holds. So this is set at the same distance. Let's just bring it in a little bit for you to see. I'm going to set this to 4. We've now got a much shorter string. That was silly because I need to bring it to 0 so you can measure the length of the string. And the length of this string now is, I guessed, about half, and it is about, that is 35 centimeters. So we've now got 35 centimeters here. Wrong button. So I've got 35 centimeters string, and we'll try something like 30 turns again, and we'll see what time we get. We'll see whether it's going to get longer or shorter. So I'm going to adjust it. We're back at 4 centimeters. Let's have a go and see what happens. My elastic band came off. Is the problem with trying to do this, that of trying to get this firm enough. I'll try and do it again. That's sad. Right, I'll have to get another elastic band. I've brought 2. We will have to measure the length again. This is, as I said, the hard bit of this experiment is trying to get this right. It's very difficult really to get this to work really well. Well, I'll try with this. We'll have another go. I'll set this to 0. So we have a length this time of 33. And we'll set this to 4. Right, we'll have a go. Here we go, ready, on the stop clock. Ready, trying to keep this going at a constant speed. Go, 1, 2, 3, 4, 5, 6, 7. 30. 13 seconds. Seemed like an eternity. Try once more. So that was 13, virtually dead, 13:01. I'll try again, see if we can do it. Here we go. Go. Stop. 10.81. I'm not so good. Somebody else doing this experiment, trying to help me, trying to measure out what's going on. So let's see now the force on this one. I've got it now much shorter. So if I put on my string, again 200 newtons required to stretch that. It should be another one. It should be the same force. I'm hoping it is. Yeah. Again, the same force required to stretch the spring, which cheers me up no end, because that means that sort of physics still basically works, and I'm always encouraged when physics works. I'm always discouraged when some of the experiments don't work, when they should, and they do when we practice them. So that's just a shorter, basically a shorter string. So what have we got here that we can actually work with? So I've got a force of 2 newtons here. 2 newtons. The radius is here 77.5 centimeters, and we've got some sort of angular velocity. Well, let's see if we can work out what this is from what we're trying to do. Now, I've got simply a time, and we can work out basically if I've done 30 turns at this, then we can work out what my velocity could be. So let's see if we can work out here this W for us. Right, so this W, we'll call it omega. Right, so it'll do here. Right, now I've got my velocity equals this number times r. Now, can we work out what that is? Well, we know that is 2 pi over t. We know the time and we know the number of revolutions. Number of revolutions here 30, divide by here, well, 15, 16 it's going to be. I know we've got 16.92. We can try 16.92. It's as accurate as we've got. So let's have our number. So we've got 30 divided by my 16.92. Gives me 1.77. So we've got here some indication then. We've got the number of turns, that is a whole turn there. It is, I need to try and get that adjusted. That's a whole turn. 2 pi is once around the circle, divided by the time there gives us a number for my omega. Caught the ruler. And now we know what the radius is. We can work out my velocity. So I can say that my velocity here is going to be 1.77 times my radius, which was 77.5, and that gives us this number times 77.5. Which gives me 137 centimeters per second. Put that into meters, then we're not that fast. 1.37 meters per second. It felt a lot faster than that, but in reality, if we consider that we're taking this and it was nearly a meter long and I was doing about 16 revolutions in 30 seconds, so it's about right. So gives us an idea about how something like this works. These are not necessarily the best way of trying to do this. Maybe we need a better experiment to try and record what's going on. So how could we try and do this a little bit better? What could we do to try and improve this? Well, I've got some other equipment that we can use. What we can use is I've got a force sensor. And if I attach that to this plastic thing, and again I'm not quite looking where I was going, I'm going to zoom out a bit, I've zoomed in too much. Then if we have the bung being whirled around the head, then we can measure here on this force sensor something that's a little bit more accurate. And what we need to also do is record this more accurately, perhaps, if I could, going through a light gate or something like that. And if I can record this then going through my light gate, then I would be able to measure quite happily the force, and if we've got then the number of revolutions here, I can work out here the revolutions per second. And it's playing around with different bits of equipment like this, which basically enables more accurate experiments to be done. So that one that we've just tried, very good for anecdotal evidence to give us some idea of what's going on. So let's see if we can summarize what we found. Looking at those figures, what do we get? Well, as I managed to make the bead here have to stretch this spring further, we therefore had to make the revolutions here faster. So as I increased to get the force to increase, I actually had to make the number of revolutions also increase. We noticed that as the radius here, we decreased the radius, therefore what I needed to do, keeping the force here constant, I then needed to basically increase the number of revolutions. And those really shouldn't be that surprising to you. So if we look at this another way, if I increase the force, the number of revolutions is going to go up, and if I keep the force the same but decrease the radius, then it's got to go basically faster. And these ideas come really with basically working out how things work in orbit and what they do. So we've got here a measurement of our angular velocity, and we can work out our centripetal acceleration. Next time we'll go into this in a bit more detail, but we've had a look at simply this idea of angular acceleration and angular velocity and radians. So next time we'll have a look at some of these in a little bit more detail. So if you like this, then please subscribe, and I'll see you again next time on A-Level Physics, topic by topic.